Okay, let's go through an example of an integral using a trig substitution. Now we use these trig substitutions when we have integrands involving square roots of certain forms. This is a square root of the form a squared minus x squared, where a is 2, since we have square root of 4 minus x squared. So in that case, if we have that type of square root, we use a trig substitution with x equals a sine theta. So in this case, 2 sine theta. Once we have x, the x substitution in terms of theta, we calculate dx by doing the derivative. Derivative of sine is cosine, so dx is 2 cosine theta d theta. Okay, so that's the first step in doing one of these integrals using a trig substitution, is identifying what type of trig substitution we have to make based on what type of square root appears in the integrand. Okay, the second step is to actually make the substitution. So what we're going to do is replace dx by the expression in terms of theta and d theta. So in the numerator here, let's put dx is equal to 2 cosine theta d theta. In the denominator, we have an x squared, so since x is 2 sine theta, x squared is 4 sine squared theta. So that's what goes here, 4 sine squared theta, that's the x squared there, and same underneath the square root, we have 4 minus 4 sine squared theta. Now this is the key step, is we make this trig substitution because now that's going to allow us to simplify that square root. In fact, it's going to make the square root disappear. So how does that work? So it's the same pattern that happens with all of these, but let's go through it in this case. So what we have here is the square, underneath the square root we can factor out a 4, so we're left with 1 minus sine squared theta. Now you should go through the steps here, but this simplifies to 2. The 4, once you take the square root, becomes a 2, and then the 1 minus sine squared theta is cosine squared. Its square root is just cosine, of course. So again, go through the steps here, and you can write it out step by step just to make sure you understand it. Okay. So where does that leave us? Let's take the integrand, now in terms of theta, and let's write that down here. Okay. So now what we have is 2 cosine theta d theta in the numerator, 4 sine squared theta, and the square root we saw simplifies to simply 2 cosine theta. Okay, so now we've made the substitution. Now the next sub-step is to simplify. Okay, so simplify by canceling terms, common terms in the numerator and denominator. So you see that we've got a 2 cosine theta in the numerator, which can cancel with this 2 cosine theta in the denominator. That's all the simplification we can do. So what we have is, let's take the 2 over 4, let's take the 4 and pull that out as 1/4. Okay? And what we're left with is d theta over sine squared theta. Okay. So that's really the second step, completing the second step, which is making the substitution and simplifying to get to what's going to be, usually in most cases, a trigonometric integral. Right? We've made a substitution with a trig function, so that's introducing trig functions into the integral, so what we have is a trig integral. So we've got to solve this trig integral somehow. So let's flip the integrand. Take a look at the integrand that we're working with, which is 1 over sine squared theta, right? So the key thing to notice here is 1 over sine is cosecant. Okay? And so if we write that integrand as, instead of 1 over sine squared, as 1 over sine quantity squared, we said that the integrand is actually cosecant squared. Okay? That's because, again, 1 over sine squared is cosecant, right? By definition. By definition of cosecant. Okay? So, our integral is actually, remember we had a constant term 1/4 outside, the integral we have to solve is cosecant squared d theta. Cosecant squared of theta d theta. And now the question is, how do we solve this? Well, now we go back to the table of trig integrals that we have. So recall that we did this material on trig substitutions after we'd gone through trig integrals, and included in that was an entire table of trig integrals. So this trig integral right here, the integral of cosecant squared, is actually just cotangent of theta. That is the antiderivative of cosecant squared. Okay? So we have the antiderivative is 1/4 cotangent theta plus c. Alright? So I'll make a note here that this is from this step right here is from the table of trig integrals. Okay? Now the last step is, we're not quite done. We have an antiderivative, but in terms of theta. The last step is to convert back to the original integral x, right? So convert the theta antiderivative to the original variable x in this case. So how do we do that? We have to take this cotangent of theta and put it in terms of x. And that's the general, in general with these examples is you're going to have a trig integral, right? We said once you do the trig substitution, you have trig functions in terms of theta. Their antiderivatives are typically going to involve trig functions. So what you have to do is take trig functions and put them, trig functions of theta, and put them in terms of x. So what we do is we're going to use the triangle corresponding to the substitution. So remember, there's 3 general types of trig substitutions. The one we did was of the form x equals a sine theta, in our case 2 sine theta. So that corresponds to a certain triangle where we've got an angle theta, and then we've got x somewhere on here, and we've got the a value on somewhere on here. So the way that you can figure that out is by putting sine of theta, which is equal to x over 2, right? If we just divide by 2 both sides here, x over 2, and note that if we go back to the original definitions of sine in terms of a right triangle, so this is a right triangle, this is opposite over hypotenuse. Okay? So x is opposite theta, and 2 is the hypotenuse. Okay? And by the Pythagorean theorem, the other leg of the triangle is going to be the square root of the hypotenuse squared minus the other leg of the triangle squared. Okay? And you note that is the exact square root that was in the original triangle. Right? That's no accident. And if you go back to the way that square root simplified, you'll notice that in this case, cosine of theta, so let's also write that here, cosine of theta is equal to adjacent over hypotenuse. So in this case, the adjacent leg to theta is the square root, which was in the integrand, and the hypotenuse is 2. And you'll note that what we did in the trig integral, the way we simplified it, is we took that square root and expressed it as 2 cosine theta. Okay? So you can also get it from this triangle in this way. But so how are we going to use it? We're going to use this triangle to figure out what cotangent is, right? Because that's what was in the antiderivative that we computed using the table of trig integrals. So cotangent of theta is the reciprocal of tangent, right? That's the definition of cotangent. Tangent, and I'll write this over here just for reference, tangent of theta is opposite over adjacent. So the cotangent is the reciprocal, meaning we flip that, and it becomes adjacent over opposite, right? And so if we go back to the triangle, this is adjacent, this is opposite, and of course this is hypotenuse. Right? So that's what we're using. So the cotangent, adjacent over opposite, is that square root expression, the 4 minus x squared, over opposite is x. Okay? So what we have is that the original integral we started with, right? So if you go back, if you flip back to the beginning, or hopefully you're taking notes as we're going through this, the original integral we started with was this one. We figured out that that's actually equal to minus 1 over 4 cotangent of theta plus c. And I think I made a mistake before. I didn't put this negative sign on the previous page. So I had neglected to leave that. But if you look that up in the trig table, which you should, you'll see there's a minus that comes out of the antiderivative of cosecant squared. Okay? So finally what we're left with is minus 1 over 4, and now we substitute what we found for the cotangent, which was 4 minus x squared over x plus c. Okay? And that's our answer.